All right, so welcome back, students. Let's go ahead and finish up the review here for section 4.9. The main thing you want to be aware of here in section 4.9 is that the general skills that you need to have here is clearly we're going to be dealing with balancing of redox problems, so you definitely want to know that. But let me just make a quick little list of the things that actually go into all of this. So one of the first things that you need to be able to do is to identify here the oxidation number of the atoms in a compound. So that means you're going to have to identify the charge, in a sense, of every single atom in a compound, because that's the way you're going to determine whether a item either lost or gained electrons. And so in redox, the main thing that we focus on is whether electrons were gained or lost in the overall reaction by any number of atoms in that reaction. And so that's one of the main things that you need to do. The other item that you need to be able to do is you need to be able to identify the half reactions. And remember, there's two half reactions. One of them here is going to be the redox, or the reduction part. And remember, reduction here is where you're going to gain electrons. And then the other half reaction is going to be the oxidation part. And the oxidation side is where you're going to lose electrons. There were a couple of acronyms, whether you want to use them or not. There was one called LEO goes GER, and then the other one was going to be the oil rig. And so either one here, this is what you want to be able to use. The LEO GER is lose electrons is oxidation, gain electrons is reduction, and then on the other side for the oil rig, oxidation is loss of electrons and reduction is the gain of electrons. Either way, you just kind of play with it, figure out which one you prefer, and go from there. The next item that you need to be able to do in this sequence here, when we go through all of this, is once you've identified the half reactions, then the next item is you're going to need to balance. So let's go ahead and put this here. You need to balance. And there's two conditions that you need to balance in. You're either going to need to balance in acidic conditions, or you're going to have to balance in basic conditions. Now, without going through all of the individual steps right now, we'll save that for the example I've got here for you in a bit. The main difference between these is going to be whether you're going to be adding water first after you've balanced everything in terms of all the atoms that are not oxygen or hydrogen, or whether you're going to add hydroxide at the end. Now, the most common one that you're going to wind up doing is the acidic. You're going to have to balance an acidic usually for most things, and then on occasion they'll ask you, can you balance in basic? Now, be prepared. I will be asking you to do both, but here's the deal. When you go with the acidic, the main thing that you're going to want to do is you're going to have to identify oxidation, separate into the half reactions, and then you're going to balance all atoms except oxygen and hydrogen. But when you get to the part where you're balancing the oxygens and the hydrogens, you're going to do the following. So whenever you've got an oxygen, and this is going to be when you have an imbalance, so you look at both sides, make sure you have the same number, and whichever side has less oxygens that makes it unequal, you're going to add a water. So here you're going to add H2O to the side for every one oxygen that is there. And as soon as you add the water, count the hydrogens that you just added. So you have to pay attention to the coefficient and the subscript for hydrogen. And then at that point, for every hydrogen here, you're going to add hydroxide or hydrogen ion to the opposite side. That way that you have the same numbers on either end. And so that's the way you distinguish that portion of things. Now, what about the basic? How does that differ? Well, the basic side is slightly different. Excuse me. On the basic side, you'll do the same balancing, identify the charges, separate into the half reactions, make sure you balance every atom except oxygen and hydrogen. You'll do the same balancing here for oxygen and hydrogen all the way through just the way you would have done for the acidic portion of things. So it includes all of the stuff that you've got here for oxygen and hydrogen. But then what you're going to do after you've done that, you go through a round of balancing there. Essentially, you're going to balance all the way to acidic. Once you've got there, at that point, you're going to count here. So let's just say balance as in acidic. So that step has to be done. But once you get that done, the next thing that you're going to do is you're going to go essentially look at for every hydrogen ion. So you're going to count the hydrogen ions. And when you've got those hydrogen ions, you're going to add here, you're going to add an OH for every hydrogen ion on both sides. And so that will allow you then to form water on one of the sides, and then that will leave the hydroxide on the opposite side. You want to go ahead and eliminate all the species that exist on both sides, those spectator-like things that occur on both sides. cancel them out, and then rewrite the equation, and you're balanced in basic. Okay, so that's all of the steps kind of just summarized really quickly. Let's do an example. I've got one for you here, so let's go ahead and do that really quick. Okay, so let's go ahead and move everything over here to the right, summarize this, put the steps there, and then I'll move this as well over here to the side. All right, so let me see if I can get this problem here on the board, and then we'll go from there. All right, so here's the problem over here on the top right, excuse me, on the top left. So you can see here, you got the entire equation here. And so what we're going to do immediately right off the bat is we're just going to go ahead and add charges to all of the atoms here that are not. Now you do have some polyatomics here. Nitrate here has a -1 charge. So remember, the total charge is the charge of the entire structure here, and then you have to use that information to find the charge of the nitrogen. We can already assume here that the charge of oxygen is a -2 because it is the more electronegative atom, so we can do that right away. Same thing over here, we're gonna have to do a similar exercise over here when we get to the HSO4. At the very end, still has a -1 total charge, but you'll need to find the charge of the sulfur here in this case. We know the charge of hydrogen, that'll be a +1, and then we can use our general knowledge using group numbers for the rest of the atoms. Okay, so let me go ahead and add the charges and get to that really quick, and then we'll go on to the next step. All right, so we have that there. Let me go see if I can zoom in on this whole thing here. That would probably give us a little bit better perspective. And so here we've got the whole thing. And now that you've identified all the charges, notice here when we start looking at items here, moving from left to right, or just whatever method you like, but you want to compare all the atoms here individually. You can see that the copper here has a +2 charge, and if I look over to the other side, copper has a +2 charge. So copper was not involved in any oxidation or reduction. The sulfur, however, here, notice here it's a -2 charge on the reactant side, but when you look over here at the right side, it's got a +6 charge. And so that's going to be one of these species that we want to pay attention to. So I'm going to go ahead and circle that right now. That's there, the +6, and I'm just going to go ahead and combine them there. That'll be important for us. And so we can identify that here in a little bit in terms of its oxidation and reduction. Okay. Keep going down the line. Notice here the nitrogen is a +5, and on the product side, we've got a +2 nitrogen over here, so that'll be the other one. Just for good measure, let's go ahead and check everything else. Notice here we've got oxygens, it's a -2 on the other side. Oxygen is a -2 in the final product, and then in the first product here, -2, so it's not the oxygen. So the other atom that's going to be involved here is going to be the, excuse me, not that one. It's going to be the nitrogen, a +5 here, and a +2. So those are the other two atoms that are involved. And so this will identify the two half reactions that we need to be worried about. So at this point, what you want to do is go ahead and identify the number of electrons that are either lost or gained, and identify if it's a reduction event or if it's an oxidation event. And so if you look at the sulfur here, you're going from a -2 all the way to a +6. And so when you look at this section here, you're going to notice that there's a difference of 8 electrons. And so in order for you to go from a -2 all the way to a +6, one little thing that I usually do is I kind of do this thing here. So here you've got oxidation up here, you've got reduction on the bottom, and then if I kind of put little hash marks here, this would be +1, +2, and I'm not going to put very many, I'm just going to put a couple just to help me identify the direction. But when we look at this here, you're going to see that if I start off with a -2, we're starting off with a point down here, let me use blue, down here at the bottom, and we're going to go in the direction of a +6, which is going to be presumably up here for a +6. Notice we went upwards, and so that's going to be in the realm of oxidation. So this first part up here in yellow, this one here is going to be oxidation. And so we'll just label that OX. And how many electrons were involved? Well, the difference between a +6 and a -2 is a total of 8. And so this means that 8 electrons here in this particular case were lost. And so we'll do that there. We'll just label it like this, and we'll use this information in the next step. Now, let's turn our attention to the nitrogen. And the nitrogen here, we've got a +5, and we're going to go all the way down to a +2. So the difference between this, 5 minus the 2, is going to be 3. So there's a difference of 3 overall. And so if we kind of look at this in the spectrum over here, we're going from a plus. I'm going to use like a gray here. So we're going to go from a +5 from up here, and then we're going to go downwards to a 2. So we're going, when we go into downward direction, we're going down in the reduction side. So this side over here in the green is a reduction event. And the difference here for this was that there was a total difference here of 3 electrons were involved. And because we're going to a lower positive charge, this is going to be that those electrons were gained. Okay, so that's the way we do that. Now that we've identified what was oxidized and what was reduced, let's separate this out into the half reaction and then balance each one separately. So let me go and separate them out and we'll be right back. All right, so we have the two half reactions here. Notice over here on the left-hand side here, we've got the oxidation, and on the right side, we've got the reduction side. You could have put the reduction on the left side or on the right side. The choice is really up to you. Now, when we're doing this, what we're going to do now is we're going to go in and identify all of the atoms, and what we're going to try to do is balance everything so that all of the atoms are balanced on both sides of the equation. So if we kind of look at this right now, all I really did was separate the half reaction. So we've got the copper sulfide, and it's going to produce these two products here. But notice here, if you look a little bit carefully, we're not too concerned with the hydrogens because we're going to resolve that here pretty soon. We do have a sulfur on the left, we have a sulfur on the right. The oxygens are going to be resolved here pretty soon as well, and we've got the electrons, that'll be resolved here pretty soon. But what we don't have on the right-hand side is copper. So notice up here, if I kind of go from here, go up to the very top right corner, notice copper existed in the formula in the reaction as a +2, but on the product side. So we got to make sure that we include that here at the bottom. So let me go ahead and include that now. So we're going to say plus, and let me go ahead and put that in the same color as before, plus Cu2+. And what I'm going to do here, just so that we can have a distinction, I'm going to go ahead and separate these out in half reactions like that. Okay, excuse me. So now that we've got everything established here, we can account for all of the atoms on either side. So notice here now when we attempt to balance everything other than the oxygen and the hydrogen, notice we got one copper on the left-hand side, we got one copper on the right, we've got one sulfur on the left, one sulfur on the right. We'll reserve the oxygen and the hydrogen here for the next step, but let's go ahead and take care of the reduction side to make sure everything's good there as well. Here, we notice that we've got one nitrogen on the left, one nitrogen on the right. We've got oxygens, but the oxygens will be balanced here in a little bit, and then the electrons will be balanced. So the only atom that we really need to be concerned about is the nitrogens on both sides, and that has been resolved. So we don't have to worry about that anymore. So that's the first thing. Balance all atoms other than hydrogen and oxygen. Now, what we're going to do is we're going to go ahead and balance the oxygens first. And so in order for us to do that, we're going to have to kind of focus in on the oxidation side. So let's kind of zoom in here a little bit. And what we're going to do is pay attention to oxygens. And so notice here on the right-hand side, we have 4 of these oxygens overall. And so because we have 4 oxygens on the right, take a look on the left, there is no oxygen at all in any of the compounds. There's only one compound, but there is no oxygen there. So we need to adjust this so that we have the same number of oxygens on the left-hand side. So since we've got 4 here, we're going to put 4 copies of water on the right. And so that's what I'll do here. So I'm going to go ahead, come in here and say plus H2O, and then we're going to add 4 copies of that. Now, as soon as we added the 4 copies of H2O, notice here we've got 8 copies of the hydrogen ion. So we're going to have to add to the right side 8 copies of hydrogen. So let me go ahead and do that. And so what I'm going to do here is zoom out a little bit. I'm going to have to move some stuff over. So let's kind of move these things over. Give us a little bit of space. Then we move this. I might have to erase that line here just to accommodate, and I'll bring it back in a second. And so let's go ahead and add the hydrogen. So plus 4H+, and then we'll separate that out for the oxidation. Now that we've done that, notice here we've got 8 hydrogens on the left. Oh, I'm sorry, we need to put an 8 here, so let's go ahead and fix that. And so here we're going to put plus 8 hydrogen ions. And so now we can balance. So we have 4 times 2 is 8 hydrogen atoms. We've got 8 hydrogen on the right. 4 times the 1 for the oxygen gives us 4 total oxygens, which are here. 1 copper, 1 sulfur, 1 sulfur. So everything is balanced. Oh, all right. So if you look at this, you would have noticed by now, you should have identified, hey, wait a second, what about this hydrogen that was already here on the left-hand side or right-hand side to begin with? Well, since we've got 1 hydrogen here, and this is probably a common error, you want to be very careful to this so you don't do it yourself. You want to make sure that you count all the hydrogen atoms on the left as you go through this to double check everything. So we had 8 here, And so we added 8, but if you forgot this hydrogen here, then now you have 9 on the right. So we actually need to reduce this 8 hydrogen ions. We need to reduce that to 7. So let's go ahead and do that now. And so what I'll do is I'll just erase it and reapply everything here. And so this would be 7 hydrogen ions. And so that would take us to a total number of appropriate atoms on both sides. Now that you've done that, let's go ahead and take care of the reduction side. So in order to do that, let me zoom in on that side of the equation. Okay, so here we go. Let's zoom in here. I'll have to move some stuff here in a little bit, but let's go ahead and move it now to get things out of the way. All right, so what we got here is we've got the nitrogen here. We got 1 nitrogen there. Now we got to resolve the oxygen. So nitrogen's already good to go, but the oxygens, we've got 3 on the left and we've got 1 on the right. So the difference between these two, because they have to be equal, so see the one on the right has 2 electrons lower in count than the one on the right, so we need to add 2 oxygens to the right, so we're going to add that in the form of water. And so in the form of water here, we're going to add plus 2H2O. And so that'll give us the required number of oxygen. So 2 times the 1 here for the subscript, that gives us 2 plus this oxygen here, gives us a total of 3 overall. That matches the left side. But now that we've added the water, now we've got 4 hydrogens here that we need to account for. Hydrogens do not exist anywhere else, so we're going to go ahead and add that over here to the right. And let me go ahead and rewrite the equation here because I did run out of space. So what we'll do here is we're going to put H, let's put that right. So here, this is going to be 4 H plus, and then you're going to wind up getting here plus the NO3 minus plus the 3 electrons, going to form NO plus the 2 waters that we have there, okay? And so with that in hand, what we're going to do at this point is now we're going to try to resolve everything. So let's kind of bring these 2 equations back together on the same screen. So I just went ahead and rewrote the equation here. So here's the full equation on the left, here's the full equation on the right. Now, you may want to write these again yourself and put them up in vertically, stack them, or you can leave them like this. And so either method's going to be fine, but what you're going to do at this point, now that you've balanced everything, you need to compare and figure out, okay, I balanced everything. The only thing I have not balanced is going to be the electrons. And so the electrons are right here. You've got 8 on the left, and you've got 3 on the right. And so you need to resolve this. So the best way to do this is find the common multiple. And so here in this case, 8 and 3 are not divisible by a common number, but they can be multiple. So what we'll do here, the easiest is to do a similar process that we had done before, and that's the crisscross method. So we're just going to multiply the entire thing. So we're going to take this entire thing here on the left, and then we're going to do the entire thing on the right, and then we're going to crisscross. So here we've got a 3, we're going to bring this up to the top, crisscross it, and at this point here we're going to say times 3 for the one on the right, and we're going to take the electrons here from the oxidation reaction, we're going to bring it up to the top, and we're going to do a times 8. And so this would be a times 8. Now that you've done the crisscross, what you're going to need to do at this point is distribute the 3 to each of the coefficients. So this would be 4 times 3, that will give you 12 waters, 3 copper sulfides, and the same thing for all the other species and the products. You're going to do the same thing here for the the reduction side of the reaction here, distributing in to each of these particular coefficients all the way through. So let me go ahead and do that for you, and I'll rewrite the equation. We'll be right back. So here is the equations. Let's go ahead and put a base to this. We're going to add them. And as we add, the reason we aligned it the way I did here is because then that kind of gives you an indication of the left side of the reaction and the right. So what you're going to look for here is common terms that you have on both sides, and then you're going to reduce and cancel as you need in a very similar way that you did for the net ionic process when you identified the spectator ions. Now there's no spectator ions here, however we can treat them like that so that we can cancel them. So let's go ahead and do that now. And so what I'll do here, I'll zoom in a little bit just to give us a better view. And we're going to do the following. So we're going to come in here and we're going to go just line by line from left to right. On the left-hand side, we've got waters. We've got 12 on the left. And in the second equation, we've got 16. So what we'll do here is we're just going to come in and we're going to subtract the lower of the 2. So the smaller number is 12. So we're going to subtract 12 from this. This will cancel that. That'll go to 0. And then we'll come to the other side and subtract 12 that we took from the other side, because we're going to subtract the smaller number to both sides. And when we do this, this actually will cancel the that, but there's going to be some remainder, and that'll give us a 4 remainder overall. And so if we continue down the process here, we'll go along the line. Now, some of these are not going to be on the other side, so we're going to skip them. So the copper sulfide here is going to be skipped because it does not exist on the right-hand side. Neither does the nitrate, but the next item that does is the hydrogens. There's 3 hydrogen ions, 32 on the left, and when you look at the right side, you've got 21. So the difference here is we're going to have to subtract 21 from the right side and do the same thing here on the left. So let's go ahead and do this on the right side first. So minus 21 hydrogens, that cancels all of that out, and so we're going to subtract here minus 21 from here. And when we do that, the number that we wind up getting here is going to be 11. And so I'll just put this in yellow right above, and so that will give us an 11 there overall. All right, and so what I'll need to do here, just to make sure this is all formal, we'll cancel this out. That'll give us the 11 there. Now we'll turn our attention to the item that remains. The only thing that remains now is to deal with the electrons. So we'll deal with the electrons. We've got 24 on the left, and on the right-hand side, we've got 24. So that's an easy thing. We can subtract 24 from both sides. That effectively cancels both of these. It goes down to 0 for both. So we don't have these species anymore. The next thing you need to do is rewrite everything as it appears. Make sure you keep the compounds that belong on the left-hand side, leave them on the left side. Those that belong on the right side, leave them on the right side. Rewrite the equation, and this should be balanced in acidic conditions. So let me go ahead and get that done for you, and then we'll be right back. So now that we've got this, then we can actually zoom out a little bit. And this equation here that we've got at the very top is the equation that is balanced here for acidic. And so I usually put this like this, and this is balanced in acidic conditions. So this would be the answer if that's what you're trying to do. Now, if you're trying to balance for basic, and this is part of the entire process, then what you want to do at this point is continue on. So you have to do everything up to this point if you're trying to balance in basic. So you do everything we just did all the way to here, and then you're going to look for the hydrogen ions. So notice here we've got hydrogen ions. We've got a total of 11. Since we've got 11, what we're going to need to do is we're going to have to add 11 hydroxides. That is, it's, in other words, for every hydrogen ion, you're going to add 1 hydroxide ion. In this case, we have 11. So we're going to add 11 hydroxide ions to both the right side and the left side. So that will allow us then to go here and add those. So here we're going to add to this side, we're going to add 11 hydroxides that we're going to add. And then we're also going to add to the other side, we're going to add 11 hydroxides over here. Now let me go and rewrite the equation for you one more time, and then we'll do the final steps to balance it out. There's only one more step after this. So here we go. We've got the final reaction. So on the left side, you've got 11 hydroxides. Remember, you've got the 11 hydrogen ions. So with these two put together, if we get this one here, and then we combine it with this is going to form water. And it's going to form 11 copies of that water. So it'll be 11 H2O, and then you're going to get the rest. And so on the right side here, you're not going to get anything identified over here. We're going to have to deal with the waters in a second. So let me show you the rest of the reaction once you write everything all the way through. You can actually do a little bit of rearranging, but let's kind of see what we get here when we combine all of that, and then rewrite the equation one more time. Okay, so here we go. So now what we got to do is kind of do one more sweep to make sure that we don't have any like terms on either side of the reaction arrow. Notice we've got 11 waters on the left-hand side, and then we've got 4 waters on the right-hand side. So what you'll need to do at this point in order to get this squared away, you go ahead and subtract the smaller number from both sides. The smaller number between 11 and 4 is 4, so we're going to subtract 4 from both sides. And so let's go ahead and do that. So we're going to do here a minus 4 of those H2O. This cancels all of that, and we'll subtract 4 waters over here as well. That will give us a total of 7. So let's go ahead and cancel the numbers out, and that'll give us 7 here as the remaining amount. And so when you take this into account, the final reaction, once you clean it all up, write it one more time, that will be the balanced equation in basic conditions. So let me write that for you, bring it one more time, and then we'll close out the video today. So here is the overall balanced reaction in basic. Let's go ahead and give that an outline of blue all the way through. So here, this is balanced in basic conditions. So put here, balanced basic. All right. So that's the review for 4.9. It is a little bit lengthy, but keep in mind the length of this video is not going to be what you're going to take in your exam, largely because I'm taking the time to kind of point things out and explain things and write things on the board. So it takes a little bit longer, but make sure you look at the steps. You want to make sure you identify the oxidation reduction at first, split them out into half reactions. Then you're going to want to go ahead and balance every atom except for oxygen and hydrogen. Balance the oxygens by adding waters appropriately to either side, or to the side that balances out the oxygens. Then add the hydrogens to the opposing side. Then balance the electrons. Make sure you got the same number on both sides. You might need to do a crisscross. Then cancel out like terms on both sides of the reaction, and then that should give you the answers that you need for the acidic. Continuing on to basic, find the hydrogen ions, add hydroxide equal in number to the hydrogen ions. Cancel out any like terms on both sides, rewrite, and then you get the balance equation that you see here. So keep studying, keep learning, and we'll see you in class.